In this module, we're going to talk about Hess's law. So, because enthalpy and consequently change in enthalpy of reaction is a state function, when we manipulate thermochemical equations, here's how we manipulate the delta H's. So when you add thermochemical equations together, just add the delta H's for each of the equations. When you reverse the thermochemical equation, make the products the reactants and vice versa, just change the sign of delta H. And if you multiply a thermochemical equation through by some number, multiply delta H of that equation by the same number. So for example, real quick, let's say we're given these two thermochemical equations with their delta H's. If we were to add these together, so watch when you add, remember if something appears on one side of the arrow in one equation and the other side of the other, it cancels. So let's see, let's do it this way. So one of these oxygens cancels one of these, leaving two behind, and that's the only thing that really cancels here. So we have on the left-hand side of the arrow two ozones, on the right two oxygens, and then two monatomic oxygens. And delta H for this will just be the sum of the delta H's for the individual reactions. So that adds up to 68 kilojoules. On the other hand, if we were to reverse this first equation, then two ozones go to three O2s. Delta H is negative 427. When we reverse it, three O2s goes to two ozones. It's positive 427 kilojoules for delta H. And then finally, if we were to multiply, say, this second equation by three O2s and six monatomic oxygens, we multiply delta H by that 3, and we get 1,490 or so. Yeah, it's kilojoules, not kelvins. Kilojoules. There we go. All right, so let's see how we do this. This is how you use Hess's law typically. You have a chemical equation that you want to find delta H for. You don't know it. You can't measure it for some reason. But you do know delta H for some other reactions. You have these thermochemical equations. The idea is that we want to be able to add up these equations so that when we add them up, we get our goal, this equation right here. And so we're going to have to, in order to do that, we're going to have to manipulate these guys. And when we manipulate these, we're going to manipulate delta H's with the rules that I just gave you. We're going to look at this in just a second, but in general, when you're doing this sort of problem, you want to find delta H for a reaction given delta H for others. What I always do is I find one species up here in my target equation that only appears in one of the thermochemical equations I'm given. And the one that pops out at me is nitrogen, N2. We need 1 N2 on the right-hand side. Here we have 4 on the right-hand side, and it doesn't appear in any of these other equations. So I know I'm going to have to divide this guy through by 4, which means I'll divide this by 4. So let's go look at that over there. So right up here, I divided through that first chemical equation by 4, and that means I'm going to divide delta H by 4. Next, I notice that there is no ammonia in my target equation, and this first one here made me have ammonia on the left. So to cancel it, I want to have 2/4 ammonia on the right. So I took this equation and I flipped it and divided through by 4. And so that changed delta H from negative 143 kilojoules to positive, and I divided by 4. Next, I know I have hydrazine, N2H4, on the left-hand side of my target equation. This one here gave me 1/4 hydrazine. I need 3/4 more. So I take this equation right here, and I flip it around. This is flipped around, multiplied by 3/4. Did the same thing for delta H. And then finally, I notice that I have 9/4 hydrogen here, and I don't have that in my target equation. So I take the last equation that I was given, multiply it through by 9/4 so that the hydrogens cancel. And here, look what happens here. So what cancels? Well, 2 ammonias and 2 ammonias cancel, right? We have, let's see, 3/4 nitrous oxide, dinitrogen monoxide here, 3/4 here. That cancels. That's nice because we don't have it in our target. What else do we have? These add up. We have waters. We have, let's see. Well, you could do it this way. 3/4 water here cancels with this. And we have 1/4 here, 9/4 here. So we subtract, we're left with 8/4 on the right, which is 2. Okay, so these guys, this cancels. We're left with 2 there. Nitrogen. These add up. 3/4 and 1/4 add up to 1. 9/4 hydrogen cancels with 9/4 hydrogen. And finally, we have 9/8 oxygen here and 1/8. So this cancels one of these. We're left with 8/8 or just 1 oxygen left. So we have these guys adding up to 1 dinitrogen tetroxide, tetrahydride, hydrazine. We have this adding up to the oxygen. And that's everything on the left. On the right, we have the nitrogen, and we have our 2 waters, because this one canceled here, and there we go. So because we divided through by 4, we divided our delta H by 4 here. We flipped it, so we changed the sign, divided by 4. We flipped this one here and multiplied by 3/4, so we did the same, changed the sign, multiplied by 3/4 for delta H. And this one we just multiplied by 9/4, so we just multiplied delta H by 9/4. When we add all these guys up, we get our answer, -623 kilojoules.